In this video, we're going to discuss trends in acidity and basicity of organic compounds. Our goals are for you to be able to predict the relative acidity or basicity of two compounds based on structural features. So compound A is more or less acidic than compound B, and then explain your reasoning, which is the second goal here, explaining your reasoning based on energetic factors. Now, in our previous video, we talked about how to use pKa data. So I asked you these questions at the end. How can you predict whether or not an acid, HA, will be a significant acid? Yeah, you can use pKa data, either that you've looked up or that you've memorized. Second, how can you predict whether or not HA or HB, two different acids, will be a stronger acid? Well, you can again use pKa data, but this is really only if HA and HB have different functional groups. For example, if I asked you what will be a stronger acid, you might be tempted to give a different answer if you didn't have pKa's memorized. A carboxylic acid has a pKa of about 5. It's a starting point. There are different structural features that can change that pKa, but 5 is a starting point for that functional group. And then ammonium has a pKa of 9. So the stronger acid has a smaller pKa. So this acetic acid, this would be the stronger acid. Let's look at a different example. So let's compare these two molecules. So we'll compare cyclohexanol to cyclohexamine. What do you think the stronger acid is? Well, hopefully you can identify that cyclohexanol has the alcohol functional group. Cyclohexamine has the amine functional group. A generic alcohol has a pKa of 16. A generic amine has a pKa of about 35. And so the alcohol will be the stronger acid because it has a smaller pKa. Let's try this example. In this example, we're looking at cyclohexanol again versus phenol. Now, if we apply our analysis from the previous slide, we see that we have two alcohols. And so we might be stuck. So they tie. Cyclohexanol certainly has a pKa of 16. Now, you might recall that I actually pointed out that the pKa of phenol, where you have this alcohol directly attached to what's called the phenyl ring. So this is called a phenyl ring. You have an alcohol directly attached to it right here. So this molecule has a special name. It's called phenol. It has a pKa of 10. So it's actually 1,000,000 times more acidic than cyclohexanol. So if you remember that, then you say, okay, phenol, smaller pKa, more acidic molecule. But if you don't remember that, then perhaps you can figure it out if you know what structural features affect acidity. So in other words, I'm asking you why. Explain why phenol is a stronger acid, 1,000,000 times stronger acid than cyclohexanol. Now, it's still not a strong acid, right? It has a positive pKa, but it's stronger than cyclohexanol. I want you to pause and I want you to consider that question. I hope that you have some explanation in mind for why phenol is more acidic than cyclohexanol. I would like to share with you a systematic way of evaluating the relative acidities of two compounds. So what you want to do is draw their conjugate bases and then consider the stability of the conjugate bases. This is because a more stable conjugate base will correspond to a stronger acid. And we learned that in both general chemistry and we discussed it again in the previous video. So the first thing we should do is imagine that we have some strong base and it deprotonates both of our acids that we're evaluating. Okay, so it's deprotonating the most acidic proton. So go ahead, try to draw the conjugate base for each molecule. Okay, so you should get something like this, where the lone pair, if you want, from the OH bond, is now on oxygen. It already had two implied lone pairs. And now you want to ask yourself, what is the difference between these two molecules? How can we evaluate which conjugate base is more stable? Well, hopefully you see that the big difference between the molecules is that the lone pair for the oxygen and phenoxide is adjacent to pi bonds. And so that makes you think, hey, we can draw resonance structures. So this lone pair can actually be shared between carbon and oxygen here. And that would displace this lone pair onto that carbon, adjacent carbon. Now, in fact, phenoxide can be, which is the name of this molecule, phenoxide, it can be described by 3 additional resonance structures. You can pause and try to draw them if you'd like. And they look like this. So what that means, what we can see here is that the phenoxide is stabilized by delocalization of charge. The charge is spread out over 4 atoms in the ring. And as we know, in almost all cases, sharing electrons lowers their energy. It makes them more stable. And a more stable conjugate base corresponds to a stronger acid. So this explains why phenol is a stronger acid than cyclohexanol. Okay, so we need more than just memorize pKa data. We need more than this. And what we need to understand are what structural features of molecules result in trends in acidity. So we're going to go ahead and tackle that now. I have a different way of explaining this than your textbook does. You can use whichever method works for you. Obviously, I have my brain, so I like this way of thinking about it. But again, I don't. Your brain might be different. So read the textbook, look at these notes, listen to how I explain it, and then try to use the methods and frameworks that work the best for you. So as we start this discussion, I want to revisit this idea about chemistry being all about electrons. So before you move on, please, for the 50 millionth time, list for me the lowest energy places for an electron to be. Well, you may have had various answers to this question, but I want to keep us focused on what's most important for our discussion today. So the lowest energy places for an electron are those that are closer to the nucleus. Let's start over here. So we can think about hybridization. So sp is lower energy than sp2 is lower energy than sp3. We've thought about s character. The more s character, the higher probability of the electron being closer to the nucleus. And then more electronegative atoms have lower energy atomic orbitals. We'll also think about electrons being spread out. When they're spread out, they are typically lower energy. So spread out can mean delocalized or described by resonance structures. And we'll expand upon this idea as we continue through this video. So now you might be wondering, and you probably are, what does this have to do with acidity and basicity? This has everything to do with acidity and basicity. I do want to reframe this statement a little bit. So previously we have used the statement that electrons go to the lowest energy orbital. And when we use that statement, we were just kind of thinking about one species, perhaps. Let's say that electrons are most stable in the lowest energy orbital. So we'll just reframe this statement just a little bit. And this is going to help us to achieve one of our large goals. And that goal is to predict between two acids, HA and HB, for example, which one is more acidic? Now, let's imagine that we treat HA and HB with a strong base, Y minus. So here we have Y minus. You can see that I'm looking down here. So the base accepts the proton. The electrons in the HA bond go to the conjugate base. Same with HB. The electrons in the HB bond go to the conjugate base. We know that the weaker, the more stable conjugate base, whether that be A minus or B minus, corresponds to the stronger acid. So what that means practically for us is that the stability of the electrons, these electrons in the conjugate bases, this determines the acidities of HA and HB. So if, for example, these electrons in A minus, if they are more stable than in B minus, then HA will be a stronger acid. So we've already actually seen that. So we saw that with phenol versus phenoxide, or excuse me, phenol versus cyclohexanol. The electron pair in phenoxide, it was lower energy because it was spread out, right? Spread out. It was delocalized as shown in these resonance structures. So the lower energy conjugate base corresponded to the stronger acid. So now we're going to move our discussion to talk about all the different structural features, that are going to affect the stabilities of those electrons in the conjugate bases. Those are our keys. And then we're going to just stay focused. More stable or weaker conjugate base means a stronger acid. Let's take a look now at this first set of data. I'll zoom in a little bit so you can see. So we have water versus hydrofluoric acid, and we can see hydrofluoric acid has a smaller pKa, and thus it is a stronger acid. So from the data, we already know that. Smaller pKa, stronger acid. But let's think about why. So I have a strong base deprotonating both of these acids, and I've drawn in their conjugate bases. Now we want to think about the stability of the electrons from the OH bond on oxygen versus the stability of the electrons from the FH bond on fluorine. Now we can probably explain the fact that fluorine, MHF rather, is a stronger acid. That means fluoride is a more stable or a weaker conjugate base. And we can explain that because we know the electrons are in a lower energy orbital. Fluorine has a higher effective nuclear charge. It's more electronegative than oxygen. So the electrons are more stable or lower energy on fluorine because it's a more electronegative atom. Now, again, this really has to do with something called effective nuclear charge, but we're more comfortable with electronegativity, so we're just going to use that as kind of a shortcut. So this is the first structural factor that we're going to consider. So I call this the main atom. So the main atom means you're looking at, the main atom is the atom directly bonded to the acidic proton. And for these two acids, the main atom is different. It was oxygen versus fluorine. So our first trend is that when the main atom is different and in the same row, the more electronegative atom is more acidic. And we already know this. We can think about another example, an additional example. We can think about the pKa of water versus ammonia. We have different main atoms, right? Different main atoms. Oxygen is more electronegative than nitrogen. So hydroxide is more stable or lower energy than amide, the conjugate base of ammonia. Thus, water is a stronger acid. Right, and in fact, water has a pKa of 16, while ammonia has a pKa all the way 35, 38, pretty high. Excellent. One factor down, a couple more to go. So in our next example, we're going to take a look at water and hydronium ion. The pKa of water is 15.7. The pKa of hydronium ion is -2. So just from that data alone, we can tell that hydronium is the stronger acid. It's more acidic. It has a lower pKa. But we'd like to understand why hydronium is more acidic than water so that we can apply that idea, that trend, to molecules with which we're unfamiliar. So let's go ahead and consider a base deprotonating both water and hydronium and draw the conjugate bases of each of these acids. Deprotonating water generates hydroxide. Deprotonating hydronium generates water. Now, we know that since hydronium is a stronger acid, it's more acidic, we have a more stable conjugate base. So water is more stable than hydroxide. And this is because the electrons are more stable in the neutral compound, right? Neutral compounds are more stable. So water is more stable than hydroxide. These electrons from water end up on hydroxide with a negative formal charge. Those electrons from hydronium end up on water, which is neutral, and so they are more stable. So what we can see here, this is our second factor. What we can see now is that the main atom, the oxygen, is actually the same, right? So we have the same main atom, but there's formal charge involved. So when the main atom is the same, a positive formal charge will result in a stronger acid. Excellent. Okay, two factors down. A couple more to go. So let's take a look at these two molecules. They're pretty similar in that they have the same number of carbons and nitrogens, but you can see that this molecule on the right, it is 10 to the, it is, wow, that was really awkward. It is 10 to the 20 times more acidic than the compound on the left. So that's amazing. So what is going on here? Well, compare the two atoms. So we have our main atoms. They're the same element, right? So this time we have the main atoms are the same element. What about them is different? Okay, they have different hybridizations. So on the left, this nitrogen, this is sp3. On the right, this nitrogen is sp hybridized. So what, you may say? All right, well, let's just go by our analysis. Let's draw a base deprotonating each of these acids. And of course, I care about the nitrogen. I highlighted that because it's the main atom. It's the atom bonded to the acidic proton. All right, let's draw the conjugate bases. Both of the conjugate bases are neutral. So that's good, right? Well, why in the world are these electrons on this nitrogen, this molecule is called acetonitrile, why are those electrons so much more stable than these? Well, these electrons end up in an sp orbital, which is lower energy than the sp3. So we have a more stable conjugate base, and that corresponds to a stronger acid. So when the main atoms are the same element, so the atom bonded to the acidic hydrogen are the same, but they have different hybridizations. Sp will be more acidic than sp2, which will be more acidic than sp3. And we have actually seen this before. So another example of this is with the carbon acids. So the alkyne has a pKa of about 25. That's not a negative sign, that's about 25. Whereas an alkene or an alkane, I'll just show an alkane here. This has a pKa of about 50. So much, much, much less acidic. And of course, the difference between these two carbons is simply their hybridization. So sp versus sp3. That means the electrons in this bond between the acidic hydrogen and carbon will end up in an sp orbital versus, oops, not those electrons, the electrons in one of these implied bonds. Let's draw it in. The electrons in that bond, they will end up in an sp3 orbital. Sp is lower energy, thus the alkyne is more acidic. Let's make sure we understand what we've been discussing for the past 10 or 15 minutes. So pause and please answer these reflection questions. Let's take a look at my answers and compare them to what you have. So the main atom, that is the atom bonded to the acidic proton. In other words, that is the atom that accepts the electrons in this bond. And the stability of those electrons determine the acidity of the acid, or they're one of the major factors that determines the acidity of the acid. All right, what are the factors that affect the acidity of the main atom? Well, when the main atom is not the same, it's different elements, so oxygen versus fluorine, and you'll see in just a second when they're in the same row. And fluorine and oxygen are both in the second row. Electronegativity affects the acidity. The more electronegative atom will correspond to the stronger acid, so HF is the stronger acid there. Formal charge. So when the main atoms are the same, so oxygen versus oxygen, and then one of them has a positive formal charge, that will be the stronger acid. Last, when the main atom is the same, but they have different hybridizations, such as sp3 versus sp in this example, the one with more S character will be more acidic. Okay, so I mentioned that same row for the electronegativity trend here. We're going to expand our thinking to look at acids where the main atoms are in different columns. So I would like for you to pause here and examine this data and ask yourselves, do the strengths of these acids follow the trends that you would expect? So the answer here is probably yes and no. So let's look at yes first. We're going to start by just checking out water versus HF. We've already looked at this, and remind ourselves how we rationalize HF being more acidic, lower pKa, more acidic than water. We rationalize that by thinking fluorine and oxygen are in the same row, and fluorine is more electronegative than oxygen. Thus, the electrons are more stable on F minus than hydroxide. And so if F minus is a more stable conjugate base, then HF is more acidic. All right, so let's take a look at the second entry. So let's look at H2S and hydrochloric acid. So we can see with a much lower pKa, 10 to the 14 times more acidic HCl is than H2S. We can rationalize that as chlorine and sulfur, they're in the same row. Here they are, have the organic chemist periodic table at the top of the screen. Chlorine is more electronegative than sulfur. Thus, the electrons are more stable in chlorine than in thiolate, which is the name for SH minus. And so HCl is a stronger acid than H2S. So when we have our main atoms, so main atom here is oxygen versus fluorine, sulfur versus chlorine. When those two atoms are in the same row, the more electronegative main atom is more acidic. We've already discussed this trend. It's right here, number 1. Now, life gets more complicated when we're looking at examples of main atoms in the same column. So let's take a look at water versus H2S. So what we see is H2S has a lower pKa, and so it is more acidic than water. Now this might be surprising to us because oxygen is more electronegative than sulfur. Well, there's a different trend that that predominates when the two main atoms are in the same column. So when the two main atoms are in the same column, it's actually atomic radius that is a more important factor in stabilizing the conjugate bases. So thiolate is more stable than hydroxide. And this is because the electrons in thiolate, the ones that came from that SH bond, they are spread out more on that big sulfur than the electrons are on hydroxide. And so because of that, H2S is more acidic than water. And this idea we're spreading the electrons out, having them on a larger atom, it's not totally coming out of left field. If we think back to the very beginning, when we listed the factors that would be important for stabilizing electrons, we said having them spread out is better. And so at that time, all we really knew about was delocalization. Delocalization being a way to spread out electrons, but also larger atoms. So when you're comparing two atoms in the same column, the larger atom can spread those electrons out more. And so the electrons are lower energy. This is an electrostatic argument. If you've taken physics, think about Coulomb's law and the stabilities of large charges versus small charges. Okay, so now let's just be sure that we observe the same trend for HF versus HCl, and we do. HCl, so we have fluorine and chlorine in the same column. HCl is more acidic than HF, and that is because the electrons are more spread out and more stable on chloride, the bigger ion, versus fluoride. And so more stable conjugate base, stronger acid. That is our mantra. More stable conjugate base, stronger acid. So let's just write this trend down now. So when we have our two atoms in the same column, the larger atom, which I know it's less electronegative, but it's atomic size that matters when the two atoms are in the same column. So larger atom, more acidic. So let's just pause and kind of have our final word on the main atom, where once again, the main atom is the atom bonded to the acidic hydrogen ion. So consider two acids, HA and HB. The main acid is the one, yes, bonded to the acidic hydrogen. If the main atoms have different elemental identity, but both atoms are in the same row, what do we look at? Yes, electronegativity. So the more electronegative atom is more acidic. An example of this would be HF versus water. If the atoms are in the same column, the bigger atom is more acidic. What's an example of this? HCl versus HF. All right, finally, this time the main atoms have the same elemental identity, but they have different formal charges. The atom with a positive formal charge is more acidic than the neutral one. Our example for here was hydronium versus water. And finally, if they have different hybridization, so the main atoms are the same element, but they have different hybridizations, then the atom with more S character, so sp more than sp2, more than sp3, is more acidic. So we looked at the protonated amine versus the protonated nitrile, but for fun, let's use carbon. So an alkyne versus an alkane. The alkyne is more acidic because it has the sp carbon versus sp3. Okay, make sure you've got this. Make sure you understand how the atom that is directly bonded to the acidic hydrogen affects the acidity of the molecule. Because from here, we're going to move on. We're going to move on now to thinking about other parts of the molecule, and we're going to call them adjacent groups. So it just means other parts of the molecule, not just the main atom. So the acidity of a particular proton can be influenced by adjacent or nearby groups in the molecule. Let's look at that by trying to explain the difference in this pKa data. So we have an alcohol, which has a pKa of 16, versus a carboxylic acid, which has a pKa of 5. Now they look really similar. It's just that this has a carbonyl, or that I have just a normal alkyl chain here. So let's understand why this might be. And so remember our mantra, stronger acid, more stable conjugate base. So when we evaluate acidity, we really need to consider the conjugate base. Let's imagine some strong base, B minus, deprotonating both of these species. And we'll go ahead and draw out their conjugate bases. So you can try if you beat me to it here. So isopropanol is converted to isopropoxide. And the acetic acid is converted to acetate. But generically, we have an alkoxide versus a carboxylate. And so, look, we already know that this is more stable than the alkoxide. How do we know that? Yes, because we can see from the pKa data that the carboxylic acid is the stronger acid. So if this is the stronger acid, then the carboxylate is more stable. How do we explain that? Well, let's go ahead and draw our lone pairs in. So the electrons that were in the OH bond, let's make them big, though they're no different than the lone pairs that were already present. We can see for the carboxylate, we have a lone pair adjacent to a pi bond. So we are able to describe this molecule by resonance structures. So this molecule can be described by resonance structures, and the charge is delocalized. Remember we said spreading out electrons, spreading out charge lowers their energy. So these delocalized electrons, represented by resonance structures, these are more stable than ones that are not delocalized. So sharing the electrons and charge lowers the energy of the molecule. More stable conjugate base, stronger acid. So you want to look for resonance structures, delocalization of charges, as a stabilizing factor in conjugate bases. And the resonance structures, these are pi effects. Okay, they involved moving pi bonds. So this summary is here for you to refer to when you're working problems, but I'm going to sort of read it aloud here. So when a molecule exhibits resonance, so delocalization of electrons and charge, and that resonance allows the charge to be spread out, then the charge structure is more stable than a comparable structure that does not have delocalized charge. So we just saw that here, right? The carboxylate, it's more stable than the alkoxide because for the carboxylate, the charge is spread out, it's delocalized. I want to point out, and this is for later, I don't have an example right now, is that resonance can stabilize either the conjugate acid or the conjugate base, whatever is charged. And you just need to rely on your knowledge that a stronger acid, so HA, corresponds to a weak conjugate base. So maybe one that is stabilized by resonance. And a weaker acid, it's going to correspond to a stronger conjugate base. Maybe one that is not stabilized by resonance. Okay, now there's going to be other effects, not just pi effects. So let's take a look at this example. So compare these two molecules. We have acetic acid and trifluoroacetic acid. So I'd like for you to pause and see if you can explain the difference in acidities between these two molecules. I think you can clearly see that trifluoroacetic acid is more acidic. It has a lower pKa and therefore it is more acidic. So you pause and try to figure out why. Now, when we examine acidity, we really want to think about conjugate base stability. That's the easiest way to do this. If the acids, for example, are charged for some reason, then you could think about the stability of the acids, but often thinking kind of along these lines here, it's the charged species that you're worried about. But if they're not, then you should really think about the conjugate bases. And most often, this method of analysis works. So if we draw acetic acid, we draw its conjugate base, it's acetate. The conjugate base of trifluoroacetic acid is trifluoroacetate. I have no idea if that's how you actually name it, but so we're going to leave it blank. But we have these two conjugate bases, and they're really similar, right? Both of them is stabilized by resonance, by the localization of charge. So clearly pi effects cannot be the answer to this question. So if we're looking at the conjugate base of trifluoroacetic acid, we know that this is more stable than acetate. So why? Yeah, it's going to have to do with fluorine, right? It has to do with fluorine because the difference between the two molecules are the fluorine atoms. I'm going to go ahead and draw out all three fluorines so you don't have to do that. Fluorine is much, much, much more electronegative than carbon. And so all of those fluorine atoms are pulling the electrons in the bond closer to themselves. So I'm just drawing on my lone pairs in. So all of those fluorines are pulling the electrons towards themselves. And so what actually happens is that they can pull electrons through multiple sigma bonds. So then pulling electrons toward itself in this bond also polarizes that bond, also polarizes this bond, and that helps to stabilize that negative charge, those electrons on the oxygens. So fluorine, it's called an inductive effect. It inductively means through the sigma bonds, through the sigma framework, it inductively shares the electrons by polarizing electrons towards itself and through the sigma bonds, right? It's a very electronegative atom. And thus it stabilizes the conjugate base. And remember our mantra, a more stable conjugate base results in a stronger acid. So let's make sure we have pulled everything together that we need to pull together here. And we're going to take a look at this example. So I have three molecules. I would like for you to pause and, based on what you've learned so far, predict the relative acidities of these three compounds. I'd like you to rank them, number 1 through 3, where 1 is the most acidic and 3 is the least acidic. Please try and come back.
I hope you paused and tried this yourself. Let's compare what you came up with what I have. So I have drawn the conjugate bases of each of these species, and you should really think about what is the difference between these molecules. And the difference is the presence or absence of a halogen. So we need to be asking ourselves what the role of these halogens are. And this halogen certainly are electron withdrawing groups, right? They are very electronegative and they are withdrawing electron density through the sigma framework. So what that serves to do is it serves to stabilize the conjugate base, right? So the halogen electron withdrawing group stabilizes the conjugate bases here. And you're going to have the more stabilization for the more electronegative atom. So fluorine is the most electronegative. So this fluorobenzoate is the strongest or the most stable conjugate base, and thus the strongest acid of the pair of the trio here. Chloro is the next strongest withdrawing group, and then hydrogen, of course, is not a withdrawing group, so this is the least acidic compound. Okay, let's try one more time. So go ahead and pause and think about which molecule on each of these pairs, so you have two different questions here, A and B, will be more acidic and why. So we have different main atoms for this first example. So we imagine some base deprotonating.
And we end up with these two conjugate bases. So now we need to think about how they're different. They, again, have different main atoms. They both certainly are stabilized by delocalization of charge, absolutely. But they both have that feature. So we really want to focus here on the main atom. So we know that sulfur and oxygen are in the same column. And within a column, the larger atom is more acidic, because that negative charge is spread out in a larger area of space. So this molecule would be more acidic. Let's take a look at the second example, example B. Again, we see that our main atom, the one bearing the acidic proton, is different. We imagine a base deprotonating that proton for both species. And we again generate two resonance stabilized or delocalized anions. Okay, so we could draw resonance structures for both of these, but the big difference between them is the main atom. And so in this case, we have a nitrogen and oxygen, which are in the same row. And within the same row, we look at electronegativity. The more electronegative atom is more acidic, because the electrons that are coming from that acidic bond, they are more stable on the more electronegative atom. Excellent. Let's take a look at this pair of questions. This is going to be maybe slightly more challenging, maybe not. Pause and take a look. So again, predict which molecule in each pair will be more acidic and explain why. Now we want to start by taking a look at the conjugate bases for each of these species. Remember our mantra: the more stable conjugate base corresponds to the strongest acid. So there are two conjugate bases. We have the same main atom, so we're going to need to think about other aspects of the molecule. And for example, we can see that the lone pair generated from deprotonating this species on the right is adjacent to a pi bond. All right, so we can describe this molecule by two additional resonance structures, so I'm only going to draw one of them. You can draw the other on your own. And so since this conjugate base is stabilized by resonance, by delocalization of charge, it is more stable, so its conjugate acid is more acidic. All right, last example here. So for this example, we're trying to decide what is more acidic, this molecule or this molecule. Now, if you recall, a long, long time ago, let's see if I can even find it here, there was an awkward slide. Okay, summary of pi effects. I said resonance can either stabilize the acid or the base, whatever is charged. Okay, and for that charged species, it's really important that the charge be delocalized. So for this last example that we're looking at right now, the acid has the charge. So let's maybe think about the acid itself. So for these acids, what is different? What is different is that one of these has this amino group. And how does this amino group interact with the rest of the molecule, where you have a lone pair adjacent to a pi bond? So perhaps we need to just sort of think about how that affects the molecule itself. So we can make a double bond here, push these over, push these electrons. I no longer like this example. So for this last example, I've decided we'll discuss it at another time. This video is running really long, and this is a pretty complicated example. So we'll discuss it later. You can try it and ask me if you have questions. All right, we're going to take a brief detour, not a detour, but just kind of look at the inverse of what we've been talking about, which is to think about which species in each pair here is the strongest base. Remember, the strongest base is going to correspond to the weakest conjugate acid. So the strongest base, A minus, will correspond to the weakest acid. So pause and take a look if you'd like. If you're with me, we can think about perhaps the conjugate acids of each of these species.